Okay, well, good evening, everybody. This is Mike Bush, and tonight we're going to be talking all about cylinders. Actually, that's a somewhat deceptive name for a webinar because there's no way I could possibly talk about all about cylinders in the time allotted tonight. But I'm going to cover a little bit about a lot of different things about cylinders, and tonight's presentation is actually going to be a little different than my usual ones because mostly I'm just going to show you a whole lot of pictures of cylinders, healthy ones, sick ones, cutaway ones, how they fail, how we monitor their condition, and that sort of thing. And I've got lots of pictures to show you. So and Charlie doesn't like me to run too long, so I'm going to try to go through this as quickly as I can, make sure we have some time for questions. Tonight we're going to be discussing, we'll start off talking about the anatomy of a cylinder, how cylinders are put together, then talk about the various tools we use for determining cylinder condition, and the pros and cons of various condition monitoring tools. We're going to talk about abnormal combustion events that can wreak havoc with cylinders, and what they look like, and how as pilots we need to learn to detect them and respond to them. Talk about various ways that cylinders fail, and how serious various failure modes are. In particular, we'll talk about maintenance-induced failures that are cylinder failures caused by something a mechanic did, which we see quite a lot of. And we'll wrap up with a few hints about how to maximize the longevity of your cylinders and minimize the risk that they're going to come apart. So let's first of all talk about the anatomy of a cylinder, how they go together. They're actually pretty complicated. But we'll just focus on some of the most important basics about how cylinders are constructed. The most important thing to understand is that aircraft cylinders have two major subassemblies: the cylinder head and the barrel. The head is made of an aluminum alloy. The barrel is made of steel. They're both machined with lots of cooling fins and so on, and lots of different interesting things. Used to be very, very difficult to manufacture cylinders. Nowadays, with computer numerically controlled machine tools, it's kind of amazing to watch how these things are put together nowadays. They put a really rough casting into this box, press a button, and 4 minutes later, out comes a completely machined cylinder head. It's really quite astonishing to watch. I visit the Continental factory every couple of years. I've been down to Superior in Dallas and Lycoming in Pennsylvania and watched these things. And it's amazing how over the last 10 years or so, the manufacture of these things have become more and more automated, and as a result, the cost of cylinders has dropped by about 50% over the last 20 years, measured in constant dollars. They're much cheaper than they were before because it's much less labor intensive to make them, but they're pretty complicated. Here's a cutaway of a Continental cylinder, actually a Continental crossflow cylinder, and you can see lots and lots of features of the cylinder, but the most important thing that I want to focus on right now is the head to barrel junction. And here's kind of a close-up of it. The steel barrel and the aluminum cylinder head basically screw together. They're threaded in what's called an interference fit. Interference fit means that when the cylinder is assembled at the factory, the barrel goes into a refrigerator and the head goes into an oven, and then when the head is nice and hot and the barrel is nice and chilled, they get screwed together, and then when the temperatures equalize, there's an interference fit on the threads that basically will will never come loose unless there's a fatigue failure, and we'll take a look at what those look like a little bit later. But at any rate, that's the procedure. It used to be that the cylinder and the barrel and the head were screwed together manually. There used to be a guy down at the TCM factory that had big leather gloves, and that was his specialty, is taking the hot head out of the oven and the cold head barrel out of the refrigerator and screwing them together. Now it's all done by a machine. It's not nearly as romantic as it used to be. But that's an interference fit. Here's a cutaway of a Lycoming barrel before it's been mated with the head, and you can see the threaded area of the barrel that's going to mate with similar threads on the head. Here's another cutaway. This is a Continental cylinder showing the exhaust valve assembly, and you can see there's a seat that's pressed into the head. That's also an interference fit. The seat is chilled in the refrigerator and pressed into the hot head to create interference fit. The exhaust valve guide, which is also an interference fit as well. Again, the guide is chilled and pressed into the hot head, and then when the temperatures equalize, that should be a junction that never comes loose. And finally, the head casting. While we're looking at this cutaway, I want to point out a couple of things to you. If you take a real close look at the valve where it contacts the seat, you will notice that the valve and the seat are cut at slightly different angles, so that the point of contact between the valve and the seat is a relatively narrow area. The art of cutting the seats just right is very, very important, because if the contact area between the seat and the valve is too great, then there's not enough pressure there to keep the interface clean, and carbon and lead and other deposits will build up on the back of the valve and cause leakage problems. On the other hand, if the contact area is too small, then the exhaust valve doesn't have an adequate heat sink to shed its heat. The whole notion of heat sink of an exhaust valve is very, very important, because during the combustion event, during the peak pressure phase, the gases in the cylinder head are very, very hot, on the order of almost 4,000 degrees Fahrenheit. And the only way that the valve can survive that sort of temperature is to have a very good heat path where it can get rid of its heat. And the path is from the face of the valve through the seat and to the cylinder head. And the cylinder head, of course, has all these cooling fins and is designed to dissipate the heat, and it has very high thermal mass. When the valve opens during the exhaust stroke, it loses its primary heat sink mechanism, because the valve is no longer in contact with the seat, and so it can't shed its heat that way. Fortunately, by the time the exhaust valve opens, the gases in the combustion chamber have cooled down to something under 2,000 degrees, but they're still pretty hot. And when the exhaust valve is open, since it can't shed its heat through contact with the seat, it has to shed its heat via a secondary path, which is via the valve stem and the valve guide and to the head. That's not nearly as effective a heat path, particularly in Continental engines, because Continentals use solid exhaust valve stems. Lycoming engines, the heat path through the stem is somewhat more effective, because Lycoming uses hollow stemmed valves that are filled with the metallic sodium, liquid sodium, and that provide a more effective heat transfer during the period that the valve is open and can't shed its heat through the primary path through the seat. But at any rate, this whole business about how exhaust valves shed their heat is very important, and the art of cutting the valve seat so that it has just the right amount of contact area with the valve, not too much, not too little, is actually quite an art. There are a variety of different valve designs. The Continentals use a very, very simple valve with a flat face and a solid stem. Lycoming valves are somewhat more exotic, a fact that is reflected in their price. And in particular, the Lycoming exhaust valves are hollow-stemmed valves that are filled with metallic sodium, which is a liquid, and sloshes around inside the hollow stem, and it provides a more effective heat transfer path when the valve is open and needs to shed its heat through the valve stem and the guide. Take a look at a cylinder for a minute. Most of our engines, except the very small ones, have 4 rings. The top 2 rings are compression rings, and their job is to provide a gas seal for the combustion chamber to prevent combustion gases from getting down into the crankcase. Each ring is about 80% effective in doing that. So by stacking 2 rings in tandem, you get a seal that has efficiency up in the high 90% range. The 3rd ring down is an oil control ring. The oil control ring's job is to provide lubrication to the walls of the cylinder. The oil control ring is a slotted ring, and it has a expander spring inside of it. You can kind of see that if you look at the little picture there, which holds the control ring against the cylinder wall with a measured tension. And the groove that the oil control ring goes into in the piston, which is the 3rd groove down, has a series of oil supply holes around the circumference of the piston. So when the engine is running, copious quantities of splash oil are splashed onto the underside of the piston, the hollow inside of the piston. That oil extrudes out of the little oil supply holes. If memory serves, a Continental piston, I think, has 8 holes around its circumference, but don't hold me to that. And the oil that comes out of those holes is then metered by the oil control ring. And as the piston goes up and down, it coats repetitively coats the cylinder walls with a thin film of oil to maintain lubrication and to prevent metal-to-metal contact between the compression rings and the cylinder wall. The tension of the expander spring is what determines how thick or thin the oil film is, and that spring tension is very critical. The 4th ring, which is down below the wrist pin, is called a scraper ring. It's not present in all engines. It tends to I think the small Lycomings lack a scraper ring, but most of the large engines have one. Its job is to prevent splash oil from reaching the cylinder walls from the crankcase side, other than by the oil control ring metering it on, and it prevents an overly thick film of oil from getting on the cylinder walls. So it basically is trying to hold splash oil away from the cylinder, except to the extent that it comes through those little holes and gets metered by the oil control ring. Here's a cutaway of a Lycoming cylinder with a piston and rings in place. We're seeing the two compression rings and the oil control ring. If you look real carefully, you can see the expander spring inside the oil control ring. It's just like a coil that runs around. And you can see that the oil control ring is a slotted ring, so that oil comes out between through the slot and gets metered onto the cylinder walls. One of the things I want you to notice is that there's a really huge gap between the piston and the cylinder wall here, and the rings are sticking way out of the piston in order to seal against the cylinder walls. This is not the way this piston and cylinder look when the engine is running. This is what they look like when the engine is cold. As the engine is started and warms up, both the cylinder barrel and the piston expand. But because the piston is made of aluminum and the cylinder barrel is made of steel, and aluminum has twice the temperature expansion coefficient that steel does, the piston develops an increasingly snug fit in the cylinder as the piston and cylinder come up to full operating temperature. And when the engine is actually running, there's a very snug fit between the piston and the cylinder walls, and the rings only have to make up a very tiny gap, a very tiny annulus between the piston and the barrel. But when the cylinder is cool, the fit between the piston and the cylinder is extremely sloppy, and the rings have to make up a big gap. This is something that we have to deal with when we're first starting the engine, and it's something we have to deal with, for example, during compression checks, which I'm going to talk about in a minute. But it's not a factor when the engine is running and up to temperature, because the fit between the piston and the cylinder is quite snug when everything is up to full operating temperature. Here's a picture of the inside of the cylinder head, and you can see the valve seats that are pressed in, and you can see the bottom of the valve guides that are pressed in. All of those, again, are interference fits. The guides and the seats are chilled. The cylinder head is heated, and then they're pressed all together. And when the temperatures equalize, it's a very tight fit that isn't going to go anywhere for the life of the cylinder. Of course, there are two valves in the cylinder, two spark plug bosses in the cylinder. The little valve is the exhaust valve. The big valve is the intake valve. Let's talk a little bit about how we monitor condition of cylinders. We've got three primary tools for cylinder condition monitoring: the compression test, borescope inspection, and digital engine monitor data analysis. The compression test is the classic test, but it's also the least accurate test. And in recent years, there has been a strong de-emphasis on using the compression test as the primary measure of cylinder condition for reasons that I will mention briefly. I'm sure all of you guys have seen a compression test done, or many of you have even done it yourself. Basically, we remove the top spark plug from the cylinder, position it at top dead center, and into the top spark plug hole we screw a little adapter that allows us to pump air into the cylinder from an air compressor. For what I assume are historical reasons, we pump air into the cylinder at a pressure of 80 psi. There's a regulator there on the left that we can use to adjust that pressure to 80 psi. We then pass that 80 psi air through a small calibrated orifice and then pump it into the cylinder. And we have another gauge at the other side of that orifice. So when we turn the air on, the cylinder is pressurized to 80 psi. And if the combustion chamber had zero leakage, if the valves were sealing perfectly and the rings were sealing perfectly, the combustion chamber would reach 80 psi, everything would be at equilibrium. The airflow would stop, and both gauges would read 80 psi. But of course, there's no such thing as a leak-free combustion chamber at the very least. We're always going to get a certain amount of leakage past the rings, particularly because when we're doing this, the cylinder is much, much cooler than it is during actual operation. And so we have this sloppy fit between the piston and the cylinder, and the rings are way out, sealing the gap between them, the annulus between them, and the rings have ring gaps that air can sneak through. So there's no such thing as a leak-free combustion chamber. So air is going to continuously leak out of the combustion chamber and have to be made up by more air being pumped in. And the greater the rate that we have to pump air into that cylinder to maintain it, to maintain its pressure, the greater the pressure drop across that little calibrated orifice between the 2 meters. So the right-hand meter is always going to read a little bit less than the left-hand meter. In this case, the right meter is reading 75 psi. The left one is reading 80 psi. So we say the cylinder is measuring out at 75 over 80 compression. And again, this is simply a measure of how much air is leaking out of the combustion chamber, at what rate that air is leaking out of the combustion chamber. The faster it's leaking out, the lower the right meter will read. Now, as I said, this test has all kinds of issues. This is one of them. This is a diagram that came out of a Continental Service Bulletin, and it's not to scale. It's sort of exaggerating the situation. But what it's illustrating is that because the piston to cylinder barrel fit is very sloppy at the temperatures at which we are doing this test, there's a big annulus between the piston and the cylinder that needs to be made up by the compression rings. And depending on where the ring gap is on the compression ring, there may be lots and lots of air that leaks through that ring gap, or there may be very little air that leaks through that ring gap. So the reading, the leakage reading that we get on the meters might be pretty mediocre in the case of that top drawing, or might be just wonderful in case of the bottom drawing. But the differences have nothing to do with cylinder condition. They have to do with just where the piston has settled inside the cylinder, and just where the ring gaps happen to be at the moment of the test. And since compression rings migrate randomly during operation, we can never predict where they're gonna be when we do the compression test. One of the things that this particular drawing was trying to illustrate in the Continental Service Bulletin was that if you bring the piston to top dead center in the normal direction of rotation, check the compression, and you don't like what you see, try to bring it to top dead center in the opposite direction of rotation, and you may very well get a much better reading. And whatever the best reading you get is the one you want to write down. But what this is emphasizing is that the compression test has an awful lot of noise on the data, and it's not a very reliable measurement of cylinder condition. There are all kinds of things that can cause low compression other than actual problems with the cylinder. We're testing the cylinder under very, very unrealistic conditions when we're doing the compression test. And there have been, hundreds of thousands of cylinders that have been pulled off of engines because of low compression readings that were just fine and didn't need to be pulled off. The compression test has a lot of false positives, so we nowadays the trend is to not pay nearly as much attention to compression readings as was the case 10 years ago. In fact, if you plot out the compressions on a particular engine year to year, you'll typically see that a particular cylinder will have a compression reading that goes up one year and down another year and then back up the third year and so on. And when the compression gets better, that doesn't mean the cylinder is unwearing or getting into better condition. It just means that there's a lot of noise on the data. And the difference between a compression of 75/80 and 68/80 is not even worth thinking about. The difference between 75/80 and 40/80 might be worth thinking about, but little changes in compression are meaningless because there's so much noise on compression readings. A low compression reading can be caused by leakage past the valves, or leakage past the rings, or by some anomaly, some artifact like what we were talking about on the previous slide that doesn't mean anything at all. So when we're doing a compression test, if the compression number we're getting is low, we want to use our ear and figure out where the air is leaking. If it's coming past an exhaust valve, for example, we'll hear air leaking out the exhaust pipe. And if it's coming past the rings, we'll hear air coming out the oil filler. And in fact, where the air is coming out, which we detect with our ear, is much more important than what the actual reading is. We can tolerate a tremendous amount of wear on the barrel and the rings, but leakage past the valves, if it's actually happening during engine operation, can lead to valve failure in flight, which can ruin your whole day. So we're much more concerned about valve leakage than we are about leakage past the rings. Another way that we can verify leakage past the rings is by watching oil consumption and watching the color of the oil and seeing how quickly it gets dark after an oil change. If we're having leakage past the rings in actual engine operation, oil consumption will be elevated because the crankcase will be pressurized and it will be blowing a lot of oil mist out the engine breather. And because of the blow-by, a lot of combustion byproducts will be getting into the crankcase, and we'll see that because in terms of the oil starting to get very dark and opaque quite early after an oil change. So we want to keep track of all of those things. One very common misconception I want to dispel before we go on to another subject is the notion that that as the compression of a cylinder goes down, the amount of power that cylinder makes goes down. In fact, that is not true. Continental ran some very interesting tests back, I think it was in 2001 or 2002, where they took I think it was an IO 550 engine, put it on their dynamometer, ran it up to full power, measured the power output. The engine is rated at 300 horsepower. Typically those engines put out more than rated power, and this particular one I think put out, I don't know, 305 or 310 horsepower. They then pulled all the cylinders and they filed the ring gaps on the compression rings oversize to intentionally increase the amount of blow-by and to reduce the compression of the cylinders. And they filed those ring gaps to where the cylinders all read 60/80 in a compression test. They ran it up on the dyno, got precisely the same horsepower. They pulled the cylinders off again, they filed the rings down so that all the compressions were 50/80 all the way around. Ran it up on the dyno, got exactly the same horsepower. Did it once again, brought all the compressions down to 40/80 by filing the ring gaps way oversized. Ran it up on the dyno, got exactly the same horsepower. They were never able to get any measurable reduction in horsepower, no matter how far they lowered the compression. Now they didn't go any further than 40/80 all around, because by the time the engine was at 40/80, there was so much blow-by and so much pressurization in the crankcase that the oil was getting totally filthy, and massive quantities of it were blowing out the breather, and they just weren't able to run the engine very long without running out of oil. But they never did get any measurable loss of horsepower. So the notion that cylinders get tired and engines get tired over time is just not correct. There are a few things that can cause an engine not to put out full power. Worn cam lobe, seriously incorrect timing on the ignition, stuff like that. But wear in the cylinders just doesn't do that. There's actually another story I heard which I can't absolutely verify, but it sounds correct to me, that some students up at the University of North Dakota Aviation program, just for the hell of it, put a Lycoming engine together and left out the compression rings altogether, so that the cylinders were all 0/80. And they ran it up and they got something like 80% of rated power with no compression rings at all. And so at any rate, leakage past the rings does not reflect itself in reduced horsepower. It reflects itself in all sorts of other mischief, but not reduced horsepower. At any rate, because the compression test has so many artifacts and there's so much noise on the data, we never ever want to remove a cylinder from an engine solely based on a poor compression rating. What we want to do is always stick a borescope in the cylinder and look around and find out what's really going on in there. Because compression tests lie, but borescope inspections don't. The borescope is the gold standard for cylinder condition nowadays. And we still do compression readings because the regs require that we do them, but what we see under the borescope is much more important than the compression readings we get. We'll talk a little bit about borescopes. This is a rigid optical borescope. It happens to be the borescope that was called out in Continental SBO 3-3, which is their service bulletin about how to do compression tests. Continental requires that a borescope inspection be done every time a compression test is done. And at the time SBO 3-3 came out, which was in 2003, this kind of borescope here was the state of the art. Has an eyepiece, it has a light source, it has a little 45-degree prism at the end of the probe, so that when you're looking through it, you're looking at a 90-degree viewing angle. In other words, you're not looking straight out the end of the probe, you're looking 90 degrees to the probe. And we stick this in a spark plug hole, typically this top spark plug hole, rotated around, and we can see pretty much everything that we need to see. And I'll show you a bunch of pictures in a minute. Nowadays, we have much better borescopes than that one. The new trend in borescopes is the electronic videoscope, like this Snap-on. This is a BK6000. It's a nice scope, and it has a little camera, a little charge-coupled camera, a CCD camera, that's very, very tiny, and that we can insert into the cylinder through the top spark plug hole and take pictures. And we see the results on a little color display. There's a USB cable, so we can plug this thing into our laptop and capture images. You can actually capture stills or movies. There are some adapters. This particular probe has a 0-degree viewing angle, but there's a little 45-degree mirror adapter you can see in the kind of the middle left side of the slide that you clip on there if you want to get a 90-degree angle, which is what we usually do when we're looking at cylinders. Here's another example of a electronic videoscope that has a little camera at the end of this probe. This is actually the borescope that I use. It's not designed as a borescope at all. It's actually a dental intraoral camera designed to take pictures of patients' teeth in a dental office, but it happens to be a superb borescope. It fits into the spark plug hole very nicely, and it creates just absolutely wonderful images. And I'll show you some of those images in a minute. But this is what I use for borescopy in my hangar. Here's some pictures. Actually, these are pictures that taken with my borescope of my a cylinder on one of my engines on my Cessna 310. This is an exhaust valve. It's in the closed position. It's in perfect shape, and I'll tell you in a few more slides how we know it's in perfect shape. But this is a real good-looking exhaust valve. It only has about 2,800 hours on it, but it's still in great shape. Here's that same exhaust valve after I rotated the prop to open the valve full open, and you can see that with a good borescope we can get a look at least part of the back side of the valve, the seating surface, and we can get a look at some of the valve guide as well. But that's a picture with the valve open. One of the interesting things we can do with a borescope is if we're looking at this valve in the open position and we turn the prop to close the valve, as the valve comes into the seat, it typically moves sideways a little bit, and you can see that as it drops into the seat. The amount that it moves sideways is a very, very good measure of just how worn the valve guide is. With a new valve guide, there's virtually no sideways movement. As the valve guide wears, we get more and more sideways movement. So you can really tell a lot with Borescope. Here's a couple of Borescope images of the cylinder barrels of a couple of different cylinders in my airplane. And these again are cylinders that have extremely high time on them, many thousands of hours. The thing on the bottom is the crown of the piston, and those two little kind of brownish stripes you see going across are the ring reversal zone, where the two compression rings come to a stop at top dead center and then reverse. That's the area of typically of maximum wear. This cylinder, you can see that the cylinder walls have no crosshatch left, so they have definitely worn quite a bit, but the walls are in pretty good shape nevertheless, and this particular cylinder was reading 75/80, the compression, the day I took this picture. Here's a picture of another cylinder. Again, you can see the piston crown in the lower right-hand corner. You can see the ring reversal area where the two rings, as high as the two compression rings reach at top dead center. And you can see that this cylinder barrel is in much worse shape. You can see a lot of vertical scoring. And this particular cylinder had a compression down in the 40s, and this is actually one that I changed out at my last annual inspection. Here's another a picture of a different spot on that same cylinder barrel, and you can see what bad condition the cylinder barrel is in. So it's really quite amazing the kind of images we can get with a borescope, and how we can tell exactly what the condition of a cylinder is, instead of just getting kind of a rough approximation, which is all the compression test gives us. One of the most important things we look at with the borescope are the condition of the valves. Again, here's a cylinder head with an exhaust valve and an intake valve. We mostly can't focus on the exhaust valves, because those are the ones that typically give us problems and burn and fail. They have to deal with a much more hostile situation than the intake valve does. This particular intake valve, or exhaust valve, the little valve on the left, is in perfect shape. The reason I say that is, if you'll notice the pattern of deposits on the face of the valve, you'll notice what looks like a perfect bullseye. The pattern is completely symmetrical, It's got some reddish exhaust deposits in the middle of the valve face, less and less deposits as you go towards the edges of the valve. That's because the valve runs coolest in the center and hottest at the edges, and the cooler the valve runs, the more deposits build up on it. So this buildup of exhaust deposits is sort of like a temperature map. And the fact that it's symmetrical tells us that this valve is running at equal temperature all the way around the circumference of the valve, which means that it's sealing properly and doesn't have any leakage or heat sinking problems. So this is a real good-looking valve. You can also tell that this particular engine has been run very, very lean, because the amount of deposits on the valve is very, very small. So this engine undoubtedly has operated lean at peak most of the time, and this is what we like to see: nice clean cylinder head, nice clean valve. Here's another exhaust valve. Again, in pretty good shape. It's got some red exhaust deposits in the center. They get much less towards the edges. The main thing is that this is a symmetrical pattern, and this tells us this valve's in good shape. Symmetry is the key. Here's a valve that's in trouble, and you'll see that there are red deposits on the valve, but towards the roughly the 2 o'clock position, there's an asymmetry there where the valve has obviously been running real hot, and there aren't deposits there the way there are the rest of the valve. This is telling us that we have a hot spot on this valve in roughly the 2 to 3 o'clock position. It isn't horrible yet. When it gets really horrible, we'll start to get a little green tinge there, and I'll show you some more horrible valves in a minute. But this is a valve that probably will not last another 50 or 75 hours before it fractures. So if you see this under the borescope, we need to pull this cylinder and revalve it. Here's a really bad valve. You can see the profound asymmetry. This valve is very, very close to failure. Again, in this case, the hot spot is in the 9 o'clock position. And if you look real closely, you can see that hot spot is just starting to get tinged with a little bit of green. If we see green, we're very close to failure. That means that the valve is running very, very hot in that area. Why is it running hot in that area? Because it's not making good contact with the valve seat. There's either metal erosion or warpage or something like that that's preventing this valve from contacting the seat in that particular position, and therefore that part of the valve face can't shed its heat during combustion, and it's running way too hot, and it's very close to failure. Here's another badly burned valve. Again, you can see where the hot spot is, and this valve we removed from the cylinder and took some photographs in different positions. If you look in the upper right-hand inset there, you'll see how badly warped this valve is. No wonder it's not making good contact with the seat. And if you look in the lower right-hand inset, you'll notice on the left side, which is the hotspot side, there's a tremendous amount of metal erosion there, almost to the point where there's a feather edge on that valve. On the right side of that valve, that same inset, you'll see that there's no metal erosion, and in fact you'll see a little shiny spot where the valve was contacting the seat. In a good valve, that shiny area will go all the way around the circumference of the valve, indicating that the valve has been contacting the seat properly and is getting burnished in that contact area. But on the left side, this valve is not contacting the seat. There is no shiny area, and in fact, there's a tremendous amount of metal erosion. Had this valve remained in service another 10 hours, that feather edge would have broken off. The compression in that cylinder would have gone to zero. It would have basically just shut down in flight, and the engine would have run extremely rough because it would be running on 5 cylinders, and the pilot would have probably declared an emergency and put the airplane down someplace. At any rate, again, symmetry is the key. Asymmetry means the valve is sick. Here's a real interesting valve came out of one of my engines. Oh God, it must have been 18 years ago. No, I'm sorry, that's not true. No, this one was only about 5 years ago. And this was an unusual valve because it actually had 2 hot spots. It had 2 burn spots. You can see they're almost diametrically opposite across the valve. This is pretty unusual. I do not often see valves that develop double hotspots like this. And if you look at the top photographs, you'll see that where the 2 red arrows are, the back of the valve is dull, indicating that it's not contacting the seat properly. And where you see the green arrows, you'll see the back of the valve is shiny, which shows that it was contacting the seat properly. But you don't actually have to see the back of the valve to tell that. You can tell all you need to know just by looking at the face of the valve, which is what we see under the borescope. And you can see that there are 2 hot spots on opposite sides of the valve. Here's the valve that's 18 years ago, back before we had borescopes and stuff. And this one went all the way to failure and shed a piece of metal, shut down the cylinder. Back then, this was a fairly common occurrence. Today, with borescope inspections, and digital engine monitors, which I'll show you in a minute, there's no excuse for ever having a failure like this, because we have the tools to catch this stuff long before it goes to failure. But that's what it looks like when it goes to failure. And this, as I said, happened close to 20 years ago, back in the dark ages, when we didn't have all the neat tools that we have today for monitoring cylinder condition. And here's what that valve looked like in the cylinder when we pulled the jug before we removed the valve from the cylinder. There's something definitely missing there. Here's a close-up of it. You can see the color pattern on that valve face, and you can almost visualize what that valve would have looked like under a borescope right before it failed. Had we been able to visualize this valve, 100 hours, 50 hours earlier, we would have definitely seen this developing. But back then, we didn't have borescopes, and we weren't able to do that kind of stuff. And so failures like this happen. But today, if you're paying attention, there's no excuse for this sort of thing happening. Here's a fractured valve. This is a Lycoming valve. That basically almost half the valve got swallowed. Here's a picture of a borescope picture of a cylinder barrel that is basically almost brand new. You can see the nice crosshatch pattern on the cylinder walls from the honing. Nice looking cylinder barrel. Here are some barrels that don't look quite so good. You can see that they have crosshatch on them, but there are areas where it's worn away, which indicates some kind of abnormal barrel wear going on. A cylinder like this is probably going to be using a lot of oil and is probably going to have to come off. Okay, let's talk a bit about digital engine monitors. The 2 big advances that we've had in cylinder condition monitoring are borescopes, which we've just talked about, and digital engine monitors. Now, I actually have a whole webinar on digital engine monitors. It's a very deep subject, so I'm only going to mention a couple things tonight. But the engine monitor is an incredibly important tool in terms of monitoring engine condition and diagnosing engine problems. And let me just show you one, and then if you're interested in this, you might want to check out the engine monitor webinar, because it is a really, really interesting subject. Here is some engine monitor data from a Cessna 210, I think it was. It's based up in Monterey, California. It was flying from someplace 4 hours away from Monterey home. And if you'll notice, the white or gray rather EGT trace, which I think is cylinder number 3, started to develop some funny stuff on it, and the funny stuff got worse and worse as the flight progressed. And if we take a look at that area that we're pointing to with the yellow arrow right during the last hour of the flight where this got real bad, let me blow that up for you so you can see some details. This is that burst blown up a little bit. And what I want to point out to you is 2 things. First of all, the amplitude of that EGT oscillation is only about 30 degrees Fahrenheit peak to peak, which means that unless that engine monitor was set in what's called normalized mode, which levels all the bars in the center and increases the sensitivity of the temperature bars, you'd never notice it. This is a 30-degree Fahrenheit oscillation on basically a 1500-degree EGT. So it's a very, very tiny percentage oscillation. But if the engine monitor is in normalized mode, which is where it should be during cruise flight, you would see this as the number 3 EGT bar rising and falling, where the other EGT bars were pretty constant. But the other thing that's even more important is to look at the frequency. This variation in EGT is not even slightly random. It is completely rhythmic. There were 20 cycles in 30 minutes. Each of those little vertical bars represents 15 minutes of flight. And if you count them very carefully, you'll notice that there are exactly 10 cycles in the first 15 minutes, exactly 10 cycles in the second 15 minutes. This thing is extremely and perfectly rhythmic. And it's very slow. 20 cycles in 30 minutes is 2/3 of a cycle per minute. So this isn't wiggling up and down rapidly. This is cycling very, very slowly and very, very rhythmically up and down. Anytime you see an EGT do that, have a slow, perfectly rhythmic cycle like this, that is the absolute unambiguous signature of a failing exhaust valve. And in fact, this 210 valve is the one that we saw earlier where we had 3 views of it. Now, the reason that a failing exhaust valve, an exhaust valve with a hot spot where some portion of the valve is not making good contact with the seat, the reason it does this, the reason that the EGT oscillates like this, is because in almost all of our piston aircraft engines, the exhaust valve is equipped with what's called a rotator cap. It's a little gizmo that sits on the top of the valve stem and underneath the rocker arm that causes the valve to rotate a small fraction of a degree every time it opens and closes. And it turns out that in a TCM engine, and this was a TSIO 520 something or other in this T210, when the engine is running at a typical cruise RPM, say 2400 RPM, the valve rotates just slightly slower than 1 cycle per minute. And as the valve rotates, when the worst spot on the valve matches up with the worst spot on the seat, we get the maximum amount of exhaust leakage, and you get a little rise in EGT. And when the valve rotates so that the worst spots are not aligned, then the leakage is a little bit less, and we get and the EGT comes down, and we get a perfectly rhythmic oscillation, which is the hallmark of a failing exhaust valve. So if you have a digital engine monitor and you run it in normalized mode and you know what you're looking for, and now you do, you can always detect a failing exhaust valve well before it actually fails. This is a really interesting series. This came from an F-33 Bonanza, and it is monitoring the progressive failure of an exhaust valve over a period of several months. And you can see that as the valve deteriorates, those oscillations in the EGT get better defined, higher amplitude, and more rhythmic, up until the last one, which was August 7th, when this thing is oscillating at literally precisely 1 cycle per minute, and it's so precise it looks like it came out of a signal generator. And that valve, I believe, if memory serves, that cylinder got pulled on August 28th or something, and this was caught before the valve failed. But you can see how this exhaust valve was telegraphing its failure via the engine monitor. If only somebody was smart enough to be looking at it and knew what they were looking for. Okay, let me move on to a couple of abnormal combustion events that can cause significant cylinder damage. These are often talked about, but often not well understood, and they're called detonation and preignition. Detonation and preignition are often confused with one another. They are totally different phenomenon. Both can cause cylinder damage, although preignition is much more dangerous than detonation is. Detonation occurs when the peak pressure of the combustion event is higher than it should be, and if the peak pressure gets high enough, then the fuel, instead of burning nice and smoothly, will develop localized pockets of abnormally rapid combustion. And those localized pockets of abnormally rapid combustion generate shock waves that can destroy the boundary layer that protect the cylinder components from melting. I mean, when you think about it, it's really quite astonishing that we can create a combustion chamber that in large part is made of aluminum. The piston crown is aluminum, the cylinder head is aluminum, with a rather low melting point, and then create a 4,000 degree combustion event without melting the piston or the cylinder head. And the reason we can do that is because there's a boundary layer of relatively cool gas that protects the piston crown and the cylinder head from those high temperatures. But if that boundary layer is disrupted by some sort of abnormally high pressure, and detonation creates that, then the aluminum components, the piston crown and the cylinder head, lose their protective boundary layer and get exposed to this incredibly hot gas and start to melt. And they can't tolerate that for very long before bad things happen. So detonation is caused by excessive peak combustion pressure and excessive peak combustion temperature. The resistance of the fuel to detonating is called its octane rating, and the higher the octane rating, the more pressure and temperature the fuel can tolerate before these localized abnormally rapid combustion pockets start to occur. So one thing that can cause detonation is substandard fuel that doesn't have full octane rating, but there are other things that can cause it. Advanced ignition timing can cause a detonation. Very high cylinder head temperatures can cause detonation. And And detonation is also not one of these things. A lot of people think of detonation as being a binary thing. Either it's detonating or it's not. It doesn't work that way. Detonation occurs in all sorts of degrees, from light detonation to severe detonation. And in fact, light detonation doesn't hurt a thing. All it does is tend to keep the cylinder, the combustion chamber, clean. But if detonation progresses far enough, it can start to compromise the components by exposing the cylinder head and the piston to temperatures that are above what they can tolerate, and they start to melt things, which is not good, obviously. Preignition is a much more severe situation. Preignition occurs when the fuel-air mixture ignites spontaneously prior to the time that the spark plug fires. And normally this happens because there's some foreign material in the combustion chamber that starts to glow red hot and becomes a glow plug that will ignite the fuel-air mixture before it's supposed to be ignited. It's obviously supposed to be ignited when the spark is thrown across the spark plug. But preignition happens when the combustion event starts before the spark plug fires, because there's something glowing red hot in the cylinder, typically some piece of foreign material, that ignites the fuel-air mixture too early. And when that happens, the stresses on the engine components are so great that no engine can withstand preignition for more than a matter of seconds. We've recently been seeing problems, for example, with Champion fine wire spark plugs where their insulators start to crack. And if a piece of the cracked insulator winds up bouncing around in the combustion chamber, it can serve as a glow plug and create a preignition event that can destroy the cylinder or destroy the piston usually, and various other things can do that. Excessive lead buildup can do that. Other sorts of foreign material that gets into the combustion chamber can do that. Let me show you very quickly a couple of preignition events, destructive preignition events that we have engine monitor data to capture. This one is out of the Cirrus SR20. It's almost a brand new Cirrus SR20. It happened to be in the UK, and the pilot applies full power for takeoff. We're looking at cylinder head temperatures here. 5 of the 6 cylinder head temperatures come up normally, up to something like 360 degrees Fahrenheit, which is typically where they ought to be at takeoff power. But one of the cylinder heads, can't tell, I think it's cylinder head number 1, the temperature just starts going ballistic, rises at an extremely rapid rate, reaches 500 degrees Fahrenheit, and flat tops. Now, it doesn't really do that. This engine monitor data came out of an Aviation system, which doesn't know how to record CHTs above 500 degrees. That basically, the needle hit the peg. In fact, what really happened, although we don't have a record of it, is that the CHT reached somewhere between 550 and 600 degrees Fahrenheit, at which point it destroyed the piston enough that cylinder could no longer sustain combustion and came crashing down. And I want to point out to you just how fast this happened, because it's really quite striking. The engine monitor set off a CHT alarm when the CHT reached 400 degrees Fahrenheit. The pilot was not trained to react properly to this, and he saw the alarm, didn't know quite what was going on. But from the time that engine monitor alarm went off at 400 degrees CHT to the time the piston got destroyed was less than 2 minutes. This happened very, very rapidly. And in fact, the CHT on that cylinder was rising more than 1 degree per second. It was an extremely rapid rise. The moral of the story here is if you ever see a cylinder head temperature exceed 400 degrees Fahrenheit and rising rapidly, you have very, very little time to react. You have to act very aggressively in order to stop this thermal runaway, or stuff is going to start melting and you're going to be in trouble. Here's the piston, and you can see what happened to the piston, how the corners melted. The #1 compression ring basically got compression ring groove got destroyed. The cylinder went to 0 compression and stopped combusting. Here's another one. This is really complicated and hard to follow, so don't worry about it. But this is another preignition event. This one happened in a Bonanza, and was even more dramatic. And basically, from the time the CHT on this particular cylinder was, say, 5, past 400 degrees Fahrenheit to the time the piston was holed, in this case was less than a minute. And of course, the moment the piston was holed, EGT instantly went to 0. CHT took a little while to drift down just because of the high thermal mass of the cylinder head. But basically, this piston got destroyed in less than a minute. And this is this is what came out of the piston. This was an extremely violent event. So we want to have engine monitors. We want to be able to set a CHT alarm to go off at 400 Fahrenheit or less. I set mine to go off at 390. And if we see a CHT exceeding 400 degrees Fahrenheit, we want to act immediately to stop the CHT increase. If you're running rich at peak, go full rich. If you're running lean at peak, pull the red knob back further. Lower the nose, open the cowl flaps, reduce power, do whatever it takes. And if the CHT continues to climb and reaches 420, you want to take drastic action, typically throttle back to idle to break the runaway, the thermal runaway. And then gradually add power just enough to keep the airplane flying and land at the next opportunity, and stick a borescope in there and see if the combustion chamber is damaged. But these are very, very violent events. Let me talk to you about some catastrophic engine failures. This Bonanza has an interesting story. It was based in Seattle, Washington at Boeing Field, and the owner forgot to remove the tow bar, had a prop strike, put the airplane in the shop. The engine was removed and sent out for a post-prop strike teardown. A new propeller and a new governor were put on the airplane. Finally, after about a month, the airplane was back together, and the mechanic turned the airplane back over to the owner, gave him some break-in instructions. The owner then proceeded to load up the airplane with himself, his girlfriend, and his girlfriend's 2 young children, and went flying out over the Puget Sound to Friday Harbor for a $100 hamburger. First flight after an engine teardown. Not a very smart move. As he was getting out over the water, the engine went into overspeed, pulled the prop control back, could not control the overspeed. Eventually, the engine was destroyed by the overspeed, and he couldn't make Friday Harbor. He couldn't make the airport on Lopez Island that he tried to reach, and wound up putting it down on a road. Now, I got to hand it to him. He did an awfully nice job of putting it down on the road. Everybody walked away. And if you look at the contour of this road as it goes off towards the horizon, you'll see, and all the phone poles or power poles, you'll see that this was not an easy place to put an airplane down. So he did an awfully good job putting the airplane down. But the whole idea of loading up an airplane with girlfriend and kids and heading out over the water on the first flight after an engine teardown showed very, very bad judgment. The likelihood of this sort of a failure is very, very high, and this airplane needed a very conservative test flight with no passengers aboard and in close proximity to an airport until there was some confidence that this engine was actually going to work. Here's what the engine looked like. It threw a rod, messed itself up pretty good. But this isn't. I mean, that's kind of what you'd expect in an overspeed condition. Here's here's some photograph of the number 2 cylinder head or cylinder heads on a Cirrus SR-22 that we manage, that fell out of the sky last Christmas on a dark night. It was flying along at 14,000 feet over the Florida Panhandle, and the engine cratered, ran out of oil. Pilot made an amazing dead stick landing in the middle of the night on a little hunk of pavement at Marianna, Florida, basically a little bitty airport with no services. Why did this happen? Airplane had just come out of an annual inspection. The shop changed the number 2 cylinder, and obviously the mechanic got distracted and didn't properly torque down the rocker covers. The left rocker cover, which is on the exhaust side, departed the premises, was never recovered. The one on the right side, if you'll look closely, you'll notice that 4 out of the 5 retaining screws are missing, and that rocker cover is just dangling by the top screw. Of course, when the rocker cover departed, all the oil followed it, and the engine had a catastrophic lubrication failure through the number 2 rod, through the top of the case, knocked one of the magnetos off, and airplane basically, the engine was complete scrap metal, and owner did an amazing job of dead stick landing this airplane. But this was clearly a mechanic-induced failure, as was the last one. Here's another really pretty one. Again, this one occurred after a top overhaul. This cylinder was let's see, the cylinder was not properly torqued down, and the hold down studs fractured, and the cylinder was liberated. Again, this happened shortly after maintenance, when cylinders were removed. It's real important to understand that when you pull a cylinder, and this is true of Lycomings and Continentals alike, the cylinders are held down at 8 points. 6 of them are studs that screw into the crankcase, and 2 of them are through bolts, which go all the way through the case to the other side and retain the cylinder on the opposite side. But the main purpose of the through bolts is not to retain the cylinders, but it's actually to hold the crankcase together, and to retain the crush on the main bearings that are set in saddles in the crankcase halves. Cylinder removal involves relieving the torque. Removing a cylinder requires relieving the torque on 2 of these through bolts. If you remove multiple cylinders, you wind up relieving torque on multiple of these through bolts. If you do that and then you turn the prop, which you basically have to do to position the piston for cylinder removal and cylinder reinstallation, there's nothing holding the crankcase halves firmly together, and you run the risk of displacing a bearing and causing lubrication failure and a catastrophic engine failure. So, the simple act of removing and reinstalling a cylinder has the potential to set up the scenario for a catastrophic engine failure. I do a lot of expert witness work, and unfortunately I've been involved as an expert witness on a whole lot of accidents, some of them fatal, where an airplane fell out of the sky because a mechanic did something wrong while replacing a cylinder. So we need to be very, very careful about who we allow to do cylinder replacement on our engines, particularly if we're replacing multiple cylinders. Cylinder removal is a moderately invasive procedure, but multiple cylinder removal is highly invasive and frequently, well, with alarming frequency, will set up the scenario for an engine failure. So we need to be very careful about that. My advice is that if you need to remove multiple cylinders from your engine, you take the airplane to an engine shop and let an engine expert work on it. There's just too much potential for maintenance-induced failures when these things are done in the field. That's my own opinion on this. It's a very controversial opinion. A lot of mechanics get mad at me when I say stuff like that. But like I said, I've just seen too many of these airplanes fall out of the sky because a mechanic did something wrong during the cylinder removal or reinstallation. This is 182 that was flying over the Badlands of Montana. Had a catastrophic cylinder head separation. Made a forced landing. The mechanic at that little field wound up getting another cylinder and putting it on, and a week later the owner was back in the air continuing his trip, and literally 30 minutes after he took off, he had the number 3 cylinder fail. We went back and looked at the photographs that were taken at the shop who was replacing number 1 cylinder, and if you look carefully, you'll see that there is exhaust stains between the critical fins on that number 3 cylinder, indicating that cylinder was starting to have a fatigue failure at the head to barrel junction as well, but the mechanic didn't notice it. To have 2 catastrophic head to barrel separations like this within 30 minutes of one another is quite extraordinary. Somebody up there wasn't liking this owner. It was a Florida-based airplane. You can see there's a lot of corrosion everywhere. The corrosion probably had something to do with setting up stress risers on these cylinders. It also happened to be the high compression version of the Skyline engine 0470U with a higher compression ratio, and we see head-to-barrel separations more frequently on that engine than on the lower compression versions of the 0470. Here's another head-to-barrel separation. Here's one that was getting ready to separate but didn't completely come free. Here's a Lycoming cylinder that had a complete separation. Something that's really important to understand is that these aluminum cylinder heads have a finite fatigue life. The longer you keep them in service, the more likely it is to have some sort of fatigue failure. Some fatigue failures are relatively benign. Some are catastrophic. But we don't want to keep these cylinder heads in service too long. The general conventional wisdom is about 2 TBOs is about all you want to keep a cylinder head in service before you send it to the scrap metal dealer. And there's really no way to inspect a cylinder and tell how much time is on it. So we have to be careful about using reconditioned cylinders. We don't want the heads to get too far along in their fatigue life. Here's one that hadn't failed yet, but the mechanic, very sharp-eye mechanic, spotted a crack in the barrel right in that key area. He spread the fins with a screwdriver, and if you look real carefully, you can see a crack in there. But this cylinder would have had a head-to-barrel separation not too much longer after that, had this sharp-eyed A&P not caught this during an angle. Here are some views from inside a cylinder head of head cracks. This is one of the things we want to look for real carefully when we do borescope inspections. Here's a crack that's developing from the exhaust valve boss, and it's starting to grow. Here's another one from the exhaust valve that's growing down towards that bottom spark plug hole. You can see. Here's one where there's 2 cracks, one that's developing from the exhaust valve boss up towards the top spark plug hole, and another crack that's initiated from the top spark plug hole. It's growing down towards that exhaust valve. Eventually, those two cracks probably would have merged. But again, this is the sort of thing that we can see with a borescope if we look nice and carefully at it. Here's the most common place that we see cracks, and this is actually off of a cylinder on my airplane. And the most common place we see cylinder head cracks is between the top spark plug hole and the fuel injector boss. These cracks are not particularly serious because once the crack goes from the spark plug hole to the fuel injector boss, it's basically stop drilled at both ends and isn't likely to go any further. The funny colors on there are dye penetrant. We frequently will get reports from mechanics of a cylinder head crack that turns out not to actually be a cylinder head crack. So anytime a shop reports a cracked cylinder head, before we let them pull the cylinder off, we require that they do a dye penetrant inspection and send us a photograph. And if there really is a crack like there was here, it will be completely obvious after the dye pen is sprayed on. One thing that's important to understand, a fundamental principle of metallurgy, is that ferrous metals and non-ferrous metals react very differently to fatigue. Ferrous metals like steel and iron have a fatigue limit, which means that if you operate those parts below a certain amount of stress, you can cycle them an infinite number of times and they won't crack. And typically ferrous metal parts like crankshafts and camshafts and connecting rods and stuff are designed to operate well below their fatigue limit. So theoretically they have an infinite fatigue life. They don't typically have an infinite life because eventually they wear out. But in principle, as long as those parts are operated within their design envelope, you can run them forever and they will never develop fatigue fractures. On the other hand, non-ferrous metal like aluminum does not have a fatigue limit. The fatigue limit is 0, which means that no matter how lightly you stress it, after a certain number of cycles, the part will crack. The lower the stress level, the higher the number of cycles it takes to develop a crack. But sooner or later, every non-ferrous metal part is going to crack, which means no crankcase can last forever without cracking, and no cylinder head can last forever without cracking. Now, sometimes the number of cycles is ridiculously large. I mean, for example, wing spars last a very, very, very long time. They won't last forever, but they last a long time because the cycle, we cycle them slowly, and they're very beefy, and so they last a long time. But cylinder heads are cycled rapidly and aggressively, and they're made of aluminum, so they're guaranteed to crack after a while. And so we don't want to push it. Like I said, the conventional wisdom is cylinder head ought to be retired after no more than about 2 TBOs. So very quickly, last 2 slides. Maximizing cylinder longevity. We want to pay obsessive attention to cylinder head temperatures. Always keep cylinder head temperatures below 400 degrees Fahrenheit, preferably below 380. In the real modern designed airplanes like the Cirrus and the Columbia and the Diamond that have really super efficient cooling systems, we'd really rather see them down below 360. But we always want cylinder head temperatures always to be below 400 degrees Fahrenheit at all times. If we let them get above that, first of all, the cylinder head longevity is compromised because at 400 degrees Fahrenheit, the tensile strength of a cylinder head is 50%, is reduced to 50% of its strength at room temperature, and as the CHT rises above that, the tensile strength drops quite rapidly. We want lean, clean operation, preferably lean at peak operation. And again, I have a whole webinar on leaning procedure, but lean at peak operation is much easier on the equipment, contrary to popular belief, the peak pressures and temperatures when you operate Lena Peak are much, much lower. It's much kinder to the cylinder heads and connecting rods and rod end bearings and main bearings and so on. So if you want to get maximum life out of an engine, you want to run at Lena Peak as much as you can. We want to fly the airplanes frequently. The single biggest reason that engines don't make TBO is because of rust. And the two things that rust are cylinder barrels and cam lobes and lifter faces. Those are the two areas that where we see the most problem with corrosion for airplanes that don't fly regularly. If you live in a highly corrosive environment and don't fly, once a week or so, you want to make sure that you use the right oil and make sure that there are anti-corrosion additives in that oil, or that you add anti-corrosive additives. And again, I've got a whole webinar on the subject of oil, which goes into all that quite a bit. Finally, minimizing the risk of catastrophic failure, cylinder failure. We want to do regular borescope inspections. Every cylinder should be inspected with a borescope at no greater than every 100 hours. For the average owner that flies 100 hours a year or less, doing a borescope inspection at annual is fine. But if you fly the airplane a lot, 200 or 300 hours a year, doing it once a year isn't enough. We want to take a look at cylinders every 100 hours at most with a borescope. Specifically, the borescope will give us around 100 hours of lead time before an exhaust valve fails. So if we aren't looking at the valve at least every 100 hours, there's a chance that we'll miss a hot spot and have the valve fail on us, and we don't want that to happen. Engine monitor data. More and more of our aircrafts are equipped with engine monitors, but most owners aren't trained how to interpret it, and most of the engine monitor data just winds up going into the bit bucket with nobody looking at it. I do have a whole webinar on the subject of engine monitors and engine monitor data interpretation, and that's something you might want to take a look at. We need to inspect very, very carefully for head cracks, particularly if the cylinder head has relatively high time on it. Every cylinder head is going to crack eventually. If you're lucky, it'll crack, between the top spark plug and the injector, and nothing terrible will happen. But if you're unlucky and it decides to crack at the head-to-barrel junction, that can really ruin your whole day. So we need to inspect cylinders very, very carefully for head cracks. Oh, I'm not sure why I have that oil leak thing, but that's true, but it's not really relevant here, so I'm going to pass over it. But we want to be very, very cautious about who we allow to remove and install cylinders, particularly if we're changing multiple cylinders or doing something like a top overhaul. I've seen so many multiple cylinder removals result in catastrophic engine failures that on the aircraft that we manage, we try to avoid doing that. And if we absolutely positively have to remove multiple cylinders, we urge the owner to take the aircraft to an engine shop and have a real engine expert do it. There's just too much potential for mechanic screw up, and we have to be very, very careful about who we allow to do that. And Charlie, that's it. I'm ready for questions. My contact information I'll leave up here, so if anybody has a question that we don't get to, or something occurs to you in the future, feel free to drop me an email, and I'll answer your question.
All right, Mike, great presentation. Ran a little longer than I think you anticipated. But let's start with Steve, because you were just talking about it. He says, what would be the first recommendation for someone like me with a Cessna 150 with stock instrumentation? What would be the first and best investment for the longevity of my 0200?
That's a very easy question. The most important investment you can possibly make is to install an engine monitor in the airplane. A lot of people think that a simple airplane like a Cessna 150 or a Cub doesn't really need an engine monitor. My view on that is absolutely the opposite. You know, if I crater a cylinder in my twin, I fly onto the destination and I think about how expensive it's going to be to fix. If you crater a cylinder in a 6-cylinder single like a Bonanza, you're going to put the airplane down at the nearest airport and change your underwear. If you have a cylinder fail in a Cessna 150 or a Cub where there's only 4 cylinders, you almost certainly are going to wind up putting the airplane down on a road or a field somewhere. So to me, it's more important to be, for a simple airplane with minimum redundancy, to be able to monitor what's going on inside those cylinders than it is for, you know, a sophisticated airplane like mine that's got goops and gobs of redundancy. So absolutely, the first thing I would do is add an engine monitor. You don't need anything fancy. A JPI EDM 700 or EDM 730 would do fine. I assure you that it will pay for itself in a year in terms of reduced maintenance costs, because it makes it so easy to diagnose problems that are very hard to diagnose without an engine monitor. So that's definitely the first thing I would recommend.
Okay, and Roy has a question. Our glider tow plane has an 0320 E2D engine, which was major overhauled last winter. We've logged about 80 hours since then. We installed a 4-probe CHT monitor at overhaul. Cylinder number 3 typically runs between 400 and 425 Fahrenheit for about 5 minutes from 1000 to 2500 AGL on every tow at a full rich mixture. The engine seems to be running fine. All the other cylinders typically run between 375 and 400. Should we be worried about cylinder number 3?
Well, you know, a tow plane is a tough situation because you're dealing with lower airspeeds. That makes it difficult to cool. I guess what I would suggest is 2 things. One is to go over the baffles and baffle seals with a fine-tooth comb and make sure that there are no spots where air can escape and bypass the cooling fins on that cylinder. And the other thing is that you might want to consider having somebody open up the main jet on the carburetor a little bit so you can get a little bit more fuel flow and a little bit better cooling for the tow operations. You know, a tow plane it's a kind of a difficult situation, but those are probably the 2 things that I would suggest. Look over the baffles really carefully and consider having the jet opened up a little bit so you can get a little bit more fuel flow to cool the CHTs down.
Okay, and Terry'd like to know what the purpose of the crosshatch in the cylinder barrel is for.
The purpose of the crosshatch in the cylinder barrel is to make it easier for oil to adhere to the cylinder walls. It's hard for oil to get a foothold if the cylinder walls are mirror smooth, and so the crosshatch is sort of a very, very tiny calibrated roughness that's put into the cylinder walls to make it easy for the oil film to adhere.
Okay, and Richard's question is, does long-term operation at low power settings, less than 65%, and lean of peak with cool CHTs, low 300 Fahrenheit, lead to cylinder glazing?
Well, it can, and if you are operating at very low power and in loiter mode, I mean, we see these in surveillance airplanes and fish spotting airplanes and pipeline patrol and so on. You probably don't want to be operating lean of peak. You probably want to be operating right at peak EGT if you're operating at very low powers. The other problem that can occur if you're operating at very low powers for a long period of time is lead contamination. If the combustion temperatures are low enough, you won't get good lead scavenging, and you'll start to get lead contamination, which is not a good thing because it can lead to stuck rings and preignition, all sorts of other things. It's easy to tell whether that's a problem or not because when you pull your spark plugs, if they have got a lot of lead buildup on them, then you can be sure that there's a lot of lead buildup elsewhere in the combustion chamber. And the solution to that is, again, to get combustion temperatures higher, probably by operating at peak EGT, and in extreme cases, putting some extra lead scavenging agent in the fuel, like Alcor TCP, which is a aftermarket fuel additive that helps with lead scavenging. Normally, that's not required, but if you're operating at real low power settings, sometimes it's a problem.
Okay, and Kenneth wanted to know about painting of head fins and barrel fins.
Let's see. I used to know something. I'm wrestling with a memory here that isn't coming forth. Generally, if you want to paint those things, you want to paint them with a very, very thin film of paint. We really would like, particularly the cylinder head fins, to retain their roughness, and we don't want to fill in the roughness with paint and have a smooth surface, because the roughness of the cylinder head fins gives them more surface area and lets them cool more effectively. I would definitely not get carried away with paint, because it can interfere with the fin's ability to transfer heat to the air.
Okay, and Nick had a question. He has an engine monitor and can export the data to graphs. Who can analyze these for me?
Well, there's actually a serious lack of expertise in this area. I do a lot of the analysis, and if he's interested in sending me his data to take a look at, I'd be glad to do it. We've actually talked about trying to set up some sort of a analysis service for engine monitor data that would sort of be analogous to an oil analysis lab. We may still do that at some point, but at the moment there really isn't anybody that in an organized way that you can send off engine monitor data to for analysis. The guys down at General Aviation Modifications Inc. down in Ada, Oklahoma do a lot of that stuff. I do a lot of it, but there aren't an awful lot of people who are knowledgeable in analyzing that data. I do have a webinar on the EAA site on that specific subject that shows a lot of case studies and would point you in the right direction in terms of being able to analyze the data. But to be honest with you, it takes some experience to really do it well. And if you have something that is interesting and needs analysis, and you want to email it to me, I'd be glad to take a look. Obviously, our managed maintenance aircraft whose maintenance we manage, we always do engine monitor data analysis anytime the airplane is going to go in for annual, and anytime there's some sort of a problem that we want to diagnose. But it's a real problem. We've got a lot of airplanes capturing this data, not very many people who have a lot of experience in analyzing it, and there's an opportunity there, whether whether my company fills it or somebody else fills it, there's a vacuum that needs to be filled for sure.
Yes, that and boroscopy, I believe, is probably another
Yep.
under.
Yeah, but
under.
boroscopy, that's true, but boroscopy is a lot easier. I can teach a mechanic everything he needs to know, or an owner, everything he needs to know about boroscopy in about 30 minutes. To really do a good job of engine monitor data analysis takes a little bit more finesse. It's a little more complicated.
Okay, and I know people like to know, and I don't think I mentioned it earlier, but we had over 300 people tonight on tonight's
cool.
webinar, so good turnout. And Rick had a question about nickel-coated aluminum cylinders. Is there a significant advantage, or should there be any concerns with them?
Well, when you say nickel, I assume you're referring to the ECI nickel carbide coating. ECI has the license for the nickel treatment. They call it Sermonil. If it's refurbishment, and the new cylinders that they make with that nickel carbide coating are called Titans. We've had very good luck with those cylinders. The compelling advantage of nickel carbide plated cylinders as opposed to conventional steel cylinders is that the nickel carbide cylinders won't rust. So if you're in a high corrosion environment, or if you operate a float plane on salt water or something like that, or if you operate a real seasonal operation where the airplane goes for months without flying, using those cylinders is kind of a no-brainer because they're immune from corrosion. Now, of course, conventional channel chrome is also immune from corrosion. The difference between the nickel carbide cylinders and the conventional channel chrome cylinders is that channel chrome cylinders are very hard to break in, and even after you've broken them in as well as you can, they usually use quite a bit of oil. Typically, if you can get oil consumption down to 1 quart in 5 hours with a chrome cylinder, you're doing really, really well. The nickel carbide cylinders break in instantly and typically have very low oil consumption. As I said, they're excellent cylinders. We've had very good luck with them, and they have a compelling advantage if the airplane is vulnerable to corrosion, either because it lives in a high corrosion area like South Florida or Houston or something, or because it flies very irregularly and spends a lot of time sitting around.
Okay, and we had a couple of questions regarding stuck valves and how you can avoid them, or the cause for valve sticking. Could you talk about that a bit?
Sure. Stuck valves are mostly a lycoming problem. We don't see them very often in Continental engines, although we occasionally will see them in some of the older Continental designs, like the O200 and C90 and stuff like that. First of all, the symptom of stuck valves is what's called morning sickness. And morning sickness means that when you first start the engine, it runs real rough. And if you have an engine monitor, you'll notice that typically that there's a cylinder that isn't firing, where the EGT is cold. And then as the engine warms up a little, the problem goes away. And that particular symptom of having a rough running engine when it's cold, when it's first started, but the roughness goes away as the engine warms up, is usually the classic tip-off to a stuck valve. And if you don't do something about it, it will progressively get worse. And if it gets bad enough, it can wind up causing some damage in flight, bent push rod or that sort of thing. And stuck valves, we see them more often in small lycomings, the 320 and 360 series lycomings, than any other engine, just because of the valve and valve guide materials that are used in those engines. There is a something called a wobble test, which Lycoming recommends doing every, depending on the engine model, every 400 hours or something like that. That is also designed to help detect stuck valves. If you do detect a stuck valve, you want to deal with it sooner rather than later, and typically a stuck valve problem can be resolved without removing the cylinder from the engine. There's a procedure where you remove the valve springs and you shove the valve into the cylinder. You catch it with some mechanical fingers through a spark plug hole. You then remount the valve guide, and then you very carefully reinsert the valve into the guide and reassemble the springs. You want to make sure that that's done by a mechanic that's done it before, but it's typically you typically can resolve a sticky valve problem without having to remove the cylinder from the engine.
Okay, well, Mike, we still got quite a few questions on the board, but I got to call it a night. And I appreciate you giving an excellent talk once again this month, and we'll look forward to the next couple of months. And if you'd like to sign up for one of the future webinars, just go to eaa.org/webinars. And also, if you want to see this presentation tomorrow night or after tonight, you can just log on sometime tomorrow afternoon. We'll have it posted at that same eaa.org/webinars website. Mike, any closing thoughts?
Well, just wanted to mention that that anyone who submitted a question that didn't have time to get answered tonight, or anybody that comes up with a question, feel free to drop me an email. I'll be glad to respond to glad to answer your question that way.
Great, thanks, Mike. And make sure you read Mike's magazine articles in Sport Aviation. Definitely a must-read every month as he covers these topics in detail. So thanks, everybody, and have a great night.
Thanks, Charlie. Thanks, everybody.